go. Speaking of transparency, back online. Happy Tuesday. Happy garbage day. Under my leadership, the garbage got taken out while my husband is out of town. Yay me. And the cans already got put back inside. So, you know what else I did? Got your homework ready. And it has been tested by at least one of the TAs and verifying the answers are correct, so I feel free to release it to folks. This is a different homework than you are used to seeing from me, and if you haven't seen any homeworks from me, then you're like, well, fine with me. But I wanted to orient you to some things that I think might be helpful in working through these problems. So you will each see questions like this. Given this minus 2 log likelihood, compute AIC for a model that contains this structure. And each of you has a different number here. So this is a randomly generated number. So the formula for AIC is minus 2 log likelihood plus 2 times the number of parameters. And so there are very specific bolded instructions in terms of what you're counting for parameters. This is following the SAS documentation. I know that other programs don't necessarily follow it, but I wanted to reiterate which parameters are on the model for the means, fixed effects side versus the model for the variance, random effects and residual side. And so if you are in ML, if you're in ML, all the parameters count. If you are in REML, only the variance model parameters count. So that is up here in the instructions as well. BIC is computed using n in the formula, natural log of n, and I want you to use level 2 sample size. So I would highly recommend that you set yourself up a spreadsheet or an R function if you're feeling extra nerdy that day and you want to be extra cool, right, Vladimir? He built himself a massive function to do this homework. Spreadsheet is fine because the point is not the math. These formulas are fairly straightforward. The point is that this is a vocabulary drill. So given 5 occasions, for instance, think to yourself, how many parameters would an unstructured R matrix take? How many parameters would a saturated means fixed effects structure take? And plug those in. So that will get you through most of it. A few model comparisons. So these can be done using functions in R. I had an example in, example 4 has a p chi-square function. Is that what it's called in R? Something like that. You can use that in Excel. You can use an example from example 4 where it uses the chi-dist function to get the exact p-values for these. So this may be a little tedious, but not hopefully too challenging. You set up your spreadsheet correctly. And in here, there are some drop-down menu questions. So this is just reviewing terminology. There are several questions that are in a similar fashion. Which of these would result in a valid likelihood ratio test? So I'm looking to see that you can take the rules for how to do likelihood ratio tests, given whether you're in ML or REML estimation, and make sure that the result would be positive. So there's really 2 rules that you want to pay attention to. What kind of model comparisons are allowed within REML versus ML? And then which model has fewer parameters and which has more? Fewer has to come first. So I'm looking for you to demonstrate an understanding of those rules. So any questions on that thus far? Okay. Now this section will be a little trickier. I'm asking you to compute various cells in R, R-core, V, or do I have V-core? Yeah, just V matrices. V we're talking about today. That's a new one, new letter for our list here. So I would refer you to the slides in lecture 4 where these models are presented. So for instance, this is how you build an R matrix for an autoregressive model. You might need to build a Toeplitz matrix. I'm not sure if I had one of those. And then what we're getting to today are the more advanced structures that have multiple pieces going into them. So that's where V comes from. It's going to be built out of multiple matrices. So the little formulas that are in here, given the pieces, you should be able to compute what each of the cells requested is. And I will remind you that if it is a number that has 2 digits that are the same, that's a variance of some kind. 2 digits that are different is either a covariance, if it's R, or a correlation, if it's R-core. And then a few more questions about various structures. So I am happy to answer questions if you want to clarify. I'm happy to listen to you walk through your logic as to how you got things, and I can confirm or deny your logic. Happy to do that. And so are the TAs, right? Anyone come to see you yet? No, he's so lonely. He sits in his office hours unattended. So you can make use of all of those resources. And chapter 4 of the book also goes over all this stuff with a different example. So any questions on that? No? All right. Then we do not have a formative assessment to do today. That will be due Wednesday, and you should be able to answer the first 2 questions for sure, and after today, the last 2. Sound good? All right. So to reorient us into what we were talking about, let me get back to where I was here. We're looking at patterns. That's what we're doing. So the end goal, the big picture, if you will, this is slide 3, is to find some kind of pattern that, as closely as possible, recreates an unstructured matrix but uses fewer parameters. That's the objective. Compound symmetry is one that we've seen so far. That is the same thing as univariate repeated measures ANOVA. That is the simplest possible structure that would be appropriate for longitudinal data. It implies constant variance over time, constant correlation over time. So that's our starting point. And this model, this structure right here, has random intercept variance in it in the output that is given as the CS parameter. So those are the same thing with different labels. We're going to see random intercept get a lot more use after today. Tell me the other patterns you remember talking about from last time that go in the middle here. And you can use the pants analogies if you want, or not. Whatever works for you. I called unstructured sweatpants, because it will always fit. I called compound symmetry skinny jeans, because it's very restrictive. What else? What other kinds of pants / R matrices do you remember? What, tapered? Yep, which one is that? Yep, starts wide and narrows. AR1. That's AR1, first order autoregressive. I called taper pants because, let me find that one here. It has 2 parameters, regardless of how many occasions there are. It has 1 total variance, so this is not a structure that differentiates between versus within. It does not partition variance. It just says you have this much total variance at each occasion, and it's 1 number. And then it estimates directly an autocorrelation parameter in a correlation metric, and occasions that are 1 unit in time apart are supposed to be correlated R. Occasions that are 2 units in time apart are correlated R squared. 3 apart is R cubed. 4 apart is R quadrupled, 4th, then 5th, and 6th, and 7th. So the problem with this, as I see it, is that the correlation decays too quickly. It's predicted at some point that this correlation is going to go to 0, and in longitudinal data, that's just not going to happen. Occasions from the same person are always going to have some correlation in most applications. So I have yet to see this fit real data, to be honest, but you will read about it in textbooks, and so that's why I throw it in here. It has a heterogeneous variance version, which would allow different variances at each occasion. This one, because it is based on the idea of a time lag, right? 1 and 2 are just as related as 2 and 3 as 3 and 4. This is only appropriate for equal interval designs. The lag has to have the same distance in order for all those constraints to make sense. There is a version of it for unequal time in which you can tell it continuous time as a variable in the software package. And I'll show you the code for that, I think, today or maybe later. Yeah, it's in there. It's in there. We'll see if we get to it today. That's what I meant. I know what's in there. So that's one. This is tapered pants. Stacy and Clinton on what not to wear never recommend tapered pants because they're not very flattering on most folks, and I agree. What else? What's the one I mispronounce consistently? Starts with a T. Yeah, topolets is how I say it, but that's not right. I called this one bootcut because depending on what kind of store you're in, that could be flared, it could be straight. Bootcut just means a little bit of flexibility towards the bottom. This one also works with the idea of a time lag. So it says that occasions 1 unit apart have a covariance of, say, C. Occasions 2 units apart have a covariance of C, separate C. So there's C for the first one, C for the second one, C for the third one. These are 3 separate estimates. So there's no squaring or cubing or fourthing, they're just separate things. That means that you can have the correlation decay a little, not decay, or even increase. It's flexible in that regard. But because it's based on time lag, you have the same constraint of equal interval occasions to use this structure, and I don't think there's a way around that. At least I've never seen one. This one also has a taupe H cousin. And let me zoom in so you can see this a little bit better. What's the H stand for? Heterogeneous. So all of them have an H variant. And it's confusing because homogeneous also starts with an H. So adding the H is really not super informative, but that's the convention. So H stands for heterogeneous. Homogeneous is the default for a lot of these. And rather than phrase the lagged relationships in terms of covariances, it phrases it in terms of correlations. It has to be that way because if your variance changes over time, your covariance must too for that reason alone. The question is, does the relationship change over time? That creates the covariances when mixed with the variances. So like this is an example of how you could build an element of an R matrix out of the ingredients. You would have the lag1 correlation times the standard deviation of one of the occasions times the standard deviation of the other. And if you're in a homogeneous structure, then you could just say the variance because all the variances are the same. So there's a shortcut in that regard. Okay, how are we doing so far? So we have sweatpants, skinny jeans, tapered, bootcut. Those are our choices as we see them thus far. We looked at an example, example 4. Do you remember the story for this? Examining changes in disease severity, fluctuations over a 7-week period, psoriasis severities to be specific, and I'm going to try not to make up any new words today, but I make no promises. Severity, is that what I did last time? Something like that? Yeah, that sounds right. Severity, I'm just going to abbreviate it. So we looked at several examples for this. Right now I'm using the R function MMRM, that's from its own little package. I'm going to have to switch to the NLME package for the later models that also involve a random intercept. And I tried to highlight within each package exactly where you would tell it what kind of structure you want. So unstructured, everything gets to be what it wants. That is type equals UN on the repeated line in SAS. That is residuals unstructured in Stata. And in the MMRM function, it is US instead of UN for reasons that I do not know. Just because, you know. The end result then is just an estimate of each possible variance per occasion and each possible covariance for pair of occasions. And we eyeballed this matrix and decided last time that the variances over time look relatively stable with a few oddballs. So it's unclear whether you would need a heterogeneous variance model because of the oddballs or not. That's an empirical question. Heterogeneous and homogeneous variance are nested comparisons. So essentially, if I have a homogeneous variance model, I have one variance. If I have a heterogeneous variance version of the same thing, how many do I have? Given 7 occasions? 7, yeah, not a trick question. So my degrees of freedom for the comparison would be what? I heard it. So I had 7 in the heterogeneous variance model. I got 1 in the homogeneous, so a difference of 6, exactly. You can think of it as a constraint. Like if I force all of these to be the same, does that hurt the model? So you're adding deviations from that one common variance to allow each of them to have their own. Correlations over time looked really high. A little bit of wiggliness around those, but for the most part, everything is greater than about 0.75 up to about 0.9 something. So we looked at compound symmetry. That one has 2 parameters. It is phrased as some kind of variance and the compound symmetry parameter. In SAS, you get the variance of the E's, and you get the compound symmetry as the variance of the random intercepts. Adding those together gets you the total variance that would be on the diagonal. In Stata, so we're talking compound symmetry for CS and SAS on the repeated line. Stata uses exchangeable for residuals. And in R, it's CS as well. They follow the convention for that one. Stata gives you the total variance, not the E variance, even though it's labeled that way. So I know, like, I don't know why they do this to you, but job security once you figure this stuff out. And it gives you cov E, which is the random intercept part. So you'd have to subtract one from the other to get to what the E part is specifically in terms of the contribution to the diagonal. And in R, it doesn't give you any of the ingredients. It's frustrating to me, because to me what's important for you to get is, like, given these two things, how do you build a pattern out of that? And without seeing the two things in isolation, I think it's more difficult to figure out how the pattern is built. But this R package does not print anything. It's like, here's your pattern, good luck. So the compound symmetry model says total variance is equal over time, built from the two pieces, the E part and the U part. Covariance is built from just the U part. And if we turn that covariance into a correlation, has a special name, interclass correlation. In this example, interclass correlation is 0.84. And do you remember what I called that in this context? For someone who didn't want to do a longitudinal study and was forced into it?
84% waste of time.
84% waste of time. Because there was already a cross-sectional component to this study in which we examined differences between people. Well, in the longitudinal sample, 84% of it was differences between people. So there's 16% new information that we gained by following these individuals over a 7-week period. It's not a great return on investment. Some people report that they have worse disease severity than other people on average, and that is responsible for 84% of the information. This structure, though, does not do a good enough job reproducing the unstructured model as indicated by a likelihood ratio test. So 28 parameters in unstructured versus 2 in compound symmetry for a difference of 26. A chi-square value of -2 log likelihood difference of 156. P-value is 0 to many decimal places. Then we looked at, let's see here, autoregressive tapered genes. That one is AR1 in SAS with parentheses. It is AR1 without parentheses in Stata, and AR1 without parentheses in R as well. I gave you the ingredients then that are being estimated for the two parameters. The total variance, which is called residual in SAS, and the autoregressive correlation. So the 0.89, that's the thing that would get squared, cubed, fourthed, fifth, and so on to build the structure. It's reported as a correlation and total variance as well in Stata. And in R, doesn't give me anything. Good luck. But here's the pattern. It says the total variance is about 0.8 all across time. And then to understand how the autoregressive part works, we need to go to R core. So there's where the autoregressive parameter shows up. It's a correlation that's being estimated directly. And 0.89554 squared is 0.801. Cubed is this one, fourth is this one, fifth is this one, and so forth. And so this model predicts that the correlation between the first and last occasion would go all the way down to 0.52. That didn't happen in the data. So this is the tapered pants problem. It goes too narrow, too much decay relative to what the data say. And we can do a likelihood ratio test to confirm that. Yep, so difference of 26 parameters, still wildly significant. What if I wanted to compare AR1 and CS? Could I do that with a likelihood ratio test? Nope, why not? Same, they each have 2, but they're 2 different patterns. Compound symmetry says 1 correlation, same over time. Autoregressive says 1 correlation, but square it, cube it, fourth it, etc. to make it work. So both the 2. Topolitz was the last one we landed on. This one gets named differently across programs. So SAS counts the entire matrix. That's why it's 7, because Toeplitz has, let me go back to the slide about this. The first parameter is the diagonal for the variances, and then it would have lagged correlations for 1, 2, 3, all the way in. Question, the AR model is significant, and so it made the model worse. Yes, let me go back to that for 1 second. There it is. So which one has to fit better, unstructured or autoregressive? In terms of -2 log likelihood, which is this first column right here. Unstructured. Now it's not going to fit best according to AIC and BIC because they have penalties for the number of parameters. Like each parameter really has to count and do a good job in order for AIC and BIC to be happy with you. So they might be unhappy with this. So for instance, if we look at BIC, who wins according to BIC right here? AR1 does. Smaller is better. But according to the difference in -2 log likelihood, the height of the data, given the model parameters, unstructured wins quite readily. So what I would say is 2 is not enough. It's not enough if you make a compound symmetry pattern. It's not enough if you make an autoregressive pattern. Okay, did that help, Zoomers? Good? All right. Okay, then Toeplitz. So 7 is the number of parameters if you go down the matrix. The first one is the variances. The second one is the first off diagonal. So there's going to be 6 off diagonals total for 7 occasions. Stata only counts the off diagonals, and so it's Toeplitz 6 for Stata instead of 7. You know, fun little differences like that. The ingredients to make the Toeplitz are listed in SAS here directly. So note the numbers. SAS understands that I'm working with weeks 2 through 7 in the data, and that's why it's numbered that way. It's going off of the variable for week that I told it to structure my pattern using. So what is being estimated is the lag 1 covariance. So 1 week apart has a covariance of this number. 2 weeks apart is this one. 3 weeks apart is that one, and so on. And these are not squared or cubed or fourth. These are just separate estimates. So they can follow whatever pattern the data need them to. The residual is the total variance. So this is another structure that doesn't separate between and within. It just sort of lumps everything together. And the pattern it creates is shown right here in the R outputs. It's shown in the other packages too, but I only printed it once. So the diagonal, first diagonal is the residual variance. That is the total variability, so residual in the sense of leftover. And then the first off diagonal, that's my lag 1 covariance. The second off diagonal is my lag 2 covariance, and so on. And then the correlations they imply are given down here. So if I stare at the correlation matrix, what do you think of this? Eyeball it. Does it look like it's doing a decent job? How do I know? Here's the answer key. This is the total variance covariance matrix in the UN model. To the left of it is what Mr. Toeplitz says. I think it's the closest one yet. Whether it's good enough, we don't know. But it looks pretty good. Survey says, oh, how would I interpret that? My likelihood ratio test. P-value of 0.048. So a comparison of the full Toeplitz R matrix versus the full unstructured.
So it is significantly worse, but not by much?
Yeah, just barely worse is what I would probably call that. Like it's just on the other side of 0.05. So it's not bad. Stata's output, by the way, does not pay attention to the fact that it's weak in here, and it just starts listing them in order. So Cove 1 through 6 as opposed to 2 through 7. I can live with that. All right, were there questions, or can I review anything?
7 again? TP7?
Because there are 7 occasions, and so to fill out the full matrix, it's that number of diagonal and then 6 off diagonals.
So we assume the homogeneous case of the integration.
This is the homogeneous case, but I can see where you're going because that's what's happening next.
Okay.
It's like, well, it's barely worse. Can we eke that over onto the other side and call this good enough? Well, let's see if the variances want to be different. Let's try that. It's a reasonable thing. Now, finding that is another question. In R, it's just taupe with no number. It just means the full thing. And this is an example of a manual likelihood ratio test that you can borrow this code to do your homework one. So all I'm doing is computing the difference in minus 2 log likelihood, computing the difference in the number of parameters so that you can just put that in as a scalar, and then p chi-square, this function, compares the two. Heterogeneous Toeplitz is not in Stata. It's not a thing. I checked once again and it's still not a thing. To make it in SAS, we add the H right there. And then we end up with the ingredients as 7 different variances and 6 different correlations. It has to be correlation because if your variance is different, that makes your covariance different for that reason alone. They're yoked together. So relative to homogeneous Toeplitz, how many terms did we add in letting the variances be different? I'll give you a hint. You answered this question like 10 minutes ago. Not a trick. So heterogeneous Toeplitz has how many variances? How many variances? 7. Homogeneous has how many? 1. So how many did we add to get to this model? 6. So that would be the ingredients for our likelihood ratio test. So there's 2 questions we can ask here. One is, did this help? Right? Because if I start with 1 variance and I turn it into 7, that should help. That's an example of adding parameters. Say, I'm sorry? Question? Okay. So the first one is, did adding 6 additional variances help? What do you think?
So it's smaller, but it's not significant.
Yeah, this is a non-significant p-value, decidedly. So do we need 7 different variances? Doesn't look like it. Didn't help. And we made things worse in terms of comparing to unstructured. Because now our degrees of freedom difference is only 15. We added a bunch of stuff we don't need. So it's a worse model significantly, not just barely, but it's moved over. So there's a little bit of a science and a little bit of an art to this. I don't think you have to try every single thing, but you can start with sort of what looks to be a reasonable pattern and maybe tweak it. Taupe H is what it is called in R as well for that. And there's the patterns that it creates. All right, how are we doing so far? Remember why we're doing this?
I'm going to have more confidence in our fixed estimates.
Yes, we are laying the groundwork to have as accurate tests of our fixed effects that we do care about as possible. This is like priming your walls before you paint them. We're doing all the background work to make sure that the paint is going to go on smoothly onto your walls or onto your nails. Take your pick. Okay. Is there a question?
I'm just saying that so we have to care about DS and p-value and
For these?
to check which model is better.
Yes. So like in these comparisons, the likelihood ratio test is only based on that much. The difference in minus 2 log likelihood and the difference in the number of parameters used. So those are the only numbers that go into this part. In addition to that, you have AIC and BIC, which are telling you in smaller is better form, essentially like relative to how complex the model is, like how did it do? And these are computed differently across packages, unfortunately. So within a package, you're internally consistent, you'll be okay. But if you try to look at output from SAS from one model versus R for another, these may not agree because they're being computed differently.
So how do they decide? For example, if AIC and BIC is saying, like, seems like better,
Mhm.
because the number is smaller. But although, like, because this has more degrees of freedom,
Mhm.
right? So again, like, the structure is not good enough because adding more does not seem like make the p-value better.
So in this case, I think I understand what you're saying. The results are sort of conflicting in terms of what you would conclude. If you go by this, well, AIC and BIC like it, it's good enough. But if you go by this, it's not good enough. And this is a test of absolute fit in this case. So we do have something to rely on. I've seen people make arguments like that, though. Well, it was technically worse, but these other things like it just fine. So we're going to go with that.
So our argument should be degrees of freedom and focus more on that. AIC and BIC would just help or not.
Yeah, I think AIC and BIC could be like tiebreakers if you're kind of not sure what to do. I've seen people just argue on the basis of that. I think it's a little bit tricky. I prefer a hypothesis test if you can get one. You have a question?
Can I think with this question this way? It's like the totally seven convenience is nested model.
Mm-hmm. Yes,
So that's why
everything is nested and unstructured. And the rest of it you said, I'm sorry?
Yeah, so that's why we have to think about this question based on the likelihood distribution test instead of AIC and BIC.
So the analog to this, by the way, for folks who've been through the structural equation modeling content, think of these as like your other fit indices. Like, well, the chi-square was significant, but I like my CFI, I like my RMSEA, I'm going to go with it. It's not different. And notice that none of that stuff is in your output for any of these programs, but it certainly could be. So if you estimate these same models using structural equation modeling software, and you can do so with constraints, I have examples of that on the Piles of Variance website for the book, you can compute CFI and RMSEA and all the other fit measures because they're just comparing different versions of a null model or a saturated model. They just don't get spit out on these because that's rarely the case that you're able to do so, only in balanced data. Okay, so yes, AIC and BIC may disagree with the likelihood ratio test. Question?
I have another question. For the R-only model, we only introduce the differences really. We don't talk about the reckoning step.
It depends on which one. So most of them do not talk about between versus within. So it's just total variance on the diagonal, and it's not split into anything. So that's why they call it E, because it's before we would have split the level 2 part out of E. So unstructured's like that, autoregressive is like that, Toeplitz is like that. All of the heterogeneous variance versions would be like that. The only one that uses random intercept and it has a between versus within partitioning is compound symmetry. And that was a perfect segue because that's where we're going next, is we're going to take compound symmetry and we're going to trick it out and make it work better. There used to be a show on MTV probably 20 years ago called Pimp My Ride. Has anyone seen this, like on reruns? It's a show in which people take old beater cars and they pimp my ride. So they'll paint them pretty colors and like put crazy stuff like an espresso machine in the trunk. And it was funny because by the time they were done, it was like, why did you upgrade this like 1997 Toyota, right? Like that was sort of a wasted effort. I believe I once saw a swimming pool get put in the back of a van. That was maybe my favorite episode. But that's kind of where it's like pimp my model. We're going to take compound symmetry, we're going to trick it out, add an espresso machine, make it better. Yeah.
I have a question for
Yeah.
the heterogeneous Toeplitz model for
Sure.
slide 13.
Slide 13, let me pull that up.
So are we making any assumptions on RT1, RT2, and RT3, or they are just estimated, whatever they are?
They're each estimated as separate things. So
So-
R1 is one thing, R2 is a separate thing, not yoked together.
Those are representing the correlation between occasions, right?
Yes.
So what if we believe that occasion 2 is more related to occasion 3 or 4 than occasion 3? So is that something that exists?
So are you talking about like within an off
Yes.
diagonal?
Yeah.
What if we don't think they should be equal?
Is there any way to constrain that if we believe that theoretically that we have two occasions that should be related than more than other pair of occasions?
Theoretically, yes. I think you could add an additional source of correlation. In terms of what's programmed into software off the shelf, I don't know of any options for that.
Can I ask if I'm understanding this right? So are you thinking like if you're collecting data in every week of the semester, you would expect the occasions that are closer together to typically be more correlated, except maybe weeks 2 and 5 there was a snowstorm, and maybe you would expect 2 and 5 to be more correlated than others?
Yeah,
Is
that's
that-
exactly.
Yes, so Zoomers, did you hear that? Should I repeat it for the recording? Okay, I should repeat it for the recording. So the question was essentially, like, can I relax this constraint or add something that would relax it that says that this R1 is different than that R1? Like there's an additional correlation for certain weeks that's not there for the others. And the example was like, what if there was a freak snowstorm this week and so it made it more related to the week that followed when there wasn't a freak snowstorm earlier in the semester? When you put it that way, I'm going to change my answer. There, because you just reminded me of a choice that's not in this lecture series because it's hurts my brain. But there's something called autoregressive moving average, ARMA, which is we're pulling out of the time series literature. An MA parameter, as it is called, is essentially like that, a shock to the system. And there are certain, it's ARMA, autoregressive moving average. It's a time series thing. You'll find that also in vector autoregressive models, I think. It shows up in a couple places. There are certain equivalencies where you can't differentiate the AR from the MA. I don't know off the top of my head what they are, but I know that there are search situations in which you can't pull those two things apart. They're redundant. But that's where I would look. MA, thank you. I did know the answer. It was just, dormant back here somewhere. And these are the only ones I'm giving you as examples in terms of what is common and what would be appropriate for longitudinal data. There's a whole bunch more of these things. Like if you look at the SAS documentation, there's like 36 kinds of these. I'm not exaggerating. Like I think I counted them once and they're all in there. There's also ones that have spatial components. So like if you're dealing with geographical data, places that are nearer to each other are going to be more related. So there's structures that have that kind of spatial component to it in addition potentially to a time component. Yeah, it gets real heavy real quick, but there's lots of them.
When you're calculating all of these models for the variance, does it matter like how big your sample size is? Because
Yes.
if you're calculating fixed effects and you keep adding parameters, you need more data. Is that true for variance too?
So the question was, what about sample size? I would say as a general rule, the more complex your pattern, the more people you need to be able to estimate it well. I think that philosophy holds. You will find out if you don't have enough people, if you get just a set of output that says, I gave up, good luck, and you get numbers with no standard errors, or you get some kind of convergence failure, not okay error message, then it's like, yeah, can't do it, sorry. With respect to the fixed effects, that is not true in these models. So in lecture 5, there is a formula by which once you figure out what your V-matrix parameters are, the solution for the fixed effects is just a fallout equation from generalized least squares. So fixed effects don't have to get searched for iteratively in the same way as variance parameters do. And so you can generally have as many of those as you want. That is no longer true once you switch into generalized versions of these models where like if you're predicting binary outcomes or count outcomes, that kind of stuff, then the fixed effects have to get found along with the variance parameters. there's no closed form for what that distribution would look like with like a Bernoulli level 1 and a normal level 2. Like that's not a thing that you can easily figure out. Too much?
We'll get to it later.
We'll get to it later. Yeah, so variance stuff breaks models, fixed effects don't. How's that for your take home? The estimation complexity is on the variance side. Right now we're talking about like types of correlation, but soon we'll be adding kinds of random effects. And that was the segue that's coming next. Okay, other things you want to talk about before we talk about a new letter. So we're going to trick out compound symmetry. That's the idea here. I have several slides in here that I'm not going to read to you because you can all read. I just wanted to sort of trap like all of my thinking and like, so I have some like cautionary tales or general principles and stuff, so I would refer you to those, like this kind of slide. All right, this one's picking up with new stuff on 15. The other side, I need to introduce you to some new terminology and ways of thinking about this. So R-only models try to directly recreate the total variance and covariance over time. The word for that we would use is marginal, and I think of that as like put back together again. Only the compound symmetry version does so by splitting it into between versus within. The others don't do that. However, there is a way to take what compound symmetry does and add things to it to make it more customizable. So this little model right here, this is an empty model that has a random intercept. We looked at that in example 3. And this is also how I would describe the compound symmetry model in this example because we only have one mean over time, because there's no change in psoriasis severity during the study on average. So what we're going to do is move this guy. We're going to move him out of the R matrix. He's going to get a new home. He's going to go live in the G matrix now. So new letter for you. Level 2, random effects live in the G matrix, their variances and covariances in particular. Level 1, the E's, their variances and covariances are going to stay in R. So U is moving out. That requires adding to the syntax. It's going to be a random statement in SAS. In Stata, it's the bar thing that we've been shutting off the whole time. And in R, it's going to require switching packages entirely. So the R matrix now is going to be only the within part of the variability across time, and the G matrix is going to hold the between part. So we're moving them apart. To put them back together again, the total, after you put them back together, is going to be stored in something called V. Because the matrices are different sizes, though, you can't just stick them together. There's a version of another matrix that shows up to handle that looks like this. Yeah. So let me show it to you in a couple different ways. This pattern up here we agreed on before was compound symmetry, right? I could write this as the letter CS here, or I could write it as random intercept variance, and that's a semantic distinction. So this is still where we're going to end up. But how we get there is through a different method of specification. We're going to put the random intercept variance over in something called G, and this matrix right now is just one number, it's a scalar. After we pull that random intercept variance out of every spot in this matrix, what's left is over here, E only. So this says the E variance specifically, the within person part of the variance, is the same over time. And within persons, there is no longer any covariance because it's over here. After you control for person mean differences, the E's are uncorrelated. This is a different way of saying it, but it's the same result as this. So, when you put them back together again, G combined with R is V up here. So this gives us now a chance to do better. Whether these things need to be 0 or something else, we can add stuff to it. We can add additional patterns of correlation beyond what is constant over time. Do these E variances need to change over time? We can ask that question. So essentially what we're doing is taking the primary source of the dependency, person-mean differences, putting that to the side, and then seeing what's left, and seeing how many patterns of correlation or heterogeneity of variance we might still need, if any. And the end result can usually be simpler, but still fit pretty well, because you factored out the most significant part of why the occasions were correlated in the first place. So what starts out as just a semantic distinction affords us opportunities to do better customization. Matrix people, if you're like, you can't just like take this and stick it everywhere in here, I'm pretty sure that's not a matrix operation, right? Stick it everywhere is not something they say over in data science, do they? No. So here's how it happens. If I have 4 occasions, then I have essentially an intercept for each person, a column of 1s. If I pre and pulse multiply my little G matrix number right here by that, then it has the right dimensions to be added to R. And if you're like, am I going to have to do this? Absolutely not. I don't do matrix anything. But for those of you that are like, yeah, I need to see the math to make this work, this is the math that makes it work. So V ends up as the marginal total result after you put back together the level 1 part that's in R, the level 2 part that's in G. Foreshadowing. This model says people differ from each other in their intercepts only, right? What if they need different change slopes? Could that happen? Yeah, guess where that's going to go? G or R? G. Yeah. So we're going to add more stuff here. We could potentially change this one too. And so we have a customization based on this approach to what does the between part look like? What does the within part look like? Not what does the whole total put together look like, because that's more challenging. So here is the most complex version that you can have, unstructured R, but with a catch. I took the random intercept variance out, stuck it over here in G. Then I could fit an unstructured model to what's left and see what the residual covariance is between each pair of occasions and what the residual variance is at each occasion. But I got to turn one of them off. Otherwise, this model would not be possible. It would be under-identified. You can't have everything be what it wants and still have one more. You got to give something back. So the end result, when you do the math to build V, is that that place where we had the 0 is due to only the random intercept variance. So the relationship between the first and last occasion is due only to random intercept. The relationships at the other occasions can be due to other stuff. So I like to estimate the unstructured model this way because then I can focus on how complicated R needs to be once I've partitioned out most of its sources of covariance over time. This one is tricky to find in software, but I'll show you what it looks like for our example data. I found it in SAS and Stata, but not anywhere in R. Not to say that it isn't, but that I did not find it. So if any of you are listening and view that as a challenge, and you're going to go find it and tell me where it is, please do. So in SAS, we're adding a new line called the random line, and that is, what would you like in your G matrix? Just an intercept, please, right now, thank you. I'm asking it to print V and V core as well as G. The repeated line then is UN6, meaning only 6 bands, and the last one, the 7th, is shut off to 0. And I'm asking for it to print R and R core, and we'll look at that output as well. In Stata, banded is the equivalent. Banded 6 shuts off the last lagged relationship, which is going to be due only to the random intercept variance. So bear with me, because I know the letters and the matrices are scary. But here's what we get. After you take out the random intercept variance, here's what's left. So the E variance at the first occasion is this. The E variance at the second occasion is this, this, and so forth. So R is purely level 1 within after you take the random intercept variance out and stick it over in G. Yep. So we have partitioned what we believe to be the between part out. That's somewhere else. This is what's left. So what's left has to be just within, just the E part. Yep, the how are you relative to your own mean? Those E's fluctuating around your own personal mean. That's the contents of this matrix, their variances and covariances. So occasions, 1 unit in time apart, have this amount of covariance. That's difficult to see how much it is because it's not standardized, so we can look at correlations. This is our core. So occasions that are 1 week in time apart, after you control for the random intercept person mean differences, they're only correlated about 0.6, 0.5, somewhere in there. 2 units in time apart, somewhat inconsistent, depends on the week. And then we get down into negative territory, so kind of some noise. So to me, it looks like the residuals might be correlated 1 week apart, 2, maybe 3, but after that, not so much. So what we can do is try to focus on, now what kind of pattern does this take purely level 1? And that pattern is likely to be able to be simpler than what it was when the U variance was stuck in there kind of messing things up. Technical term. So if I take this R level 1 within person matrix of E variances and covariances, and I take my random intercept variance, which is now sitting all by itself in something called G, and I stick this number everywhere in here, then V is my total. And this is the exact same thing as an unstructured R-only model. We just build it using pieces instead. Question?
So I'm thinking, because I'm going to try to use R for the homework. And from what I understand, the reason we want to calculate an unstructured model is because we test the other models against it
Yes.
to see, which one does the most parsimonious job of explaining the variance. If I'm testing models that include a random intercept, and I can't calculate the unstructured n-1 model in R, since the unstructured n model is identical to the unstructured n-1, can I do my model comparisons against the unstructured n model? Even
Yes.
though, okay, because
Yeah.
they're equivalent.
They are equivalent.
Oh, good. Okay.
Yeah. So the question was, this is another way of getting to the same point of UN. If my software doesn't do this one, can I just do the other version that's straightforward, R only? Yes. They are likelihood equivalent. They will generate the same results. Yeah. This is more for convenience to try to figure out, if we're focusing on the pattern of the E's, that's probably can be a simpler pattern. Because it looks like, for instance, at 6 weeks apart or 5 weeks apart, there's barely any correlation left. So here is the way we can get to compound symmetry. This is the unstructured analog. There's the compound symmetry analog. It is the same thing. So another way of saying compound symmetry is random intercept in G plus the diagonal variance components. That's what it's called in R. So now in Stata, we have something new. The lack of something. There used to be a word right there. It was no constant, because up to this point, I've been shutting off the G matrix. Now I'm letting it be there because by default, when you put your model in mixed and you tell it how your data are organized, it gives you a random intercept. So the default in this is to have a random intercept variance at a minimum in G to describe between person differences at level 2. Then the question is, what kind of R structure do you want? Independent is the simplest one. This says there is no residual correlation after you factor out individual differences in the means. That's it. The same options before that gave us W correlation in covariance form and in correlation form now refer to the V matrix instead of R. So Stata does show you the result that's put back together again, as does SAS. In R, I had to switch to a different package and a different function. I'm using the NLME package and the LME function within it. That is because that is the only way I have seen to have both random effect variances and correlation patterns at the same time in R. The other ones don't allow both. I think GLS technically does, but this one works just fine. So the model setup is a little bit different. We pick up this additional option, random equals squiggle 1 bar sub ID. That says I would like a random 1. What's a random 1? Intercept. Yeah, that's my U0 variance I'm asking for right there. A random 1. And no correlation pattern. This is independent or diagonal residual variances, no covariances. So I asked it to build the matrices so you can see the patterns, but this is what you get by default. It gives you 2 standard deviations, not variances. One for the intercept, one for the E residuals. Here's my fixed intercept. We've been ignoring that most of the time. So here's G, that one number. That's my level 2 intercept variance. If I take that and stick it everywhere in here, then you get the result of V. And there's my intra-class correlation of 0.84 that I got before. This model is the same thing as compound symmetry, just structured a different way so that we can have more flexibility in what R is. In terms of pants analogies, this is like going to a tailor. Stacy and Clinton always recommended tailoring because if you can buy the cheapest suit and get it to fit you perfectly, you will look like $1 million. Fit is everything. In order to do that, you have to buy your clothes to fit the largest part of you, take them to someone who knows what they're doing, and then they can tailor down, make the pants shorter or bring the waist in, whatever you need to do. I get the sense that we've had enough of matrices for today. Can I tell you a story instead? Would that be okay? This is professional development for those of you who are going to be going on internship and job interviews. The moral of this story is bring 2 suits. Okay? My first job interview when I was trying to be a professor, this was the winter of 2005 into 2006. I was fortunate enough to get 3 job interviews. I interviewed at the University of Nebraska first, then I went to Syracuse University, and then I interviewed at Penn State where I was currently a postdoc. And I went shopping. I had to get a big girl suit. I have a big girl interview coming up, right? So I went all over Christmas break to every spot I could think of in Omaha, and I ended up getting 2 suits. One was at a fancy, expensive suit store, more than I had spent on any outfit in my life. It was light brown with these orange pinstripes. It was really kind of distinctive. He spoke to my, love of flair, if you will. And so I got that tailored to fit me. And then I thought, well, I should have a backup suit. So on the JCPenney clearance rack, I found a sort of plain Jane black suit that was very affordable, and I got that tailored too, right? Put them both in my bag. First day of my interview, I'm supposed to have breakfast in my hotel at 7:30 in the morning. Put on the big, fancy, expensive suit, right? Because that's the day my job talk was going to be. Job talks, of course, is the main part of your interview. And I bend over to pick up my bag, and I hear, I had ripped the seam of my pants straight down my butt the entire way. Burst open. I'm like, okay, guess it's suit number 2. So I quickly change clothes. I come downstairs a few minutes late and apologize. Fortunately, the person picking me up had a sense of humor about it. I had my pants in my hand because I took them to the hotel. I was like, can I get these fixed today? And they're like, oh, it'll take a few days turnaround. They're not going to be fixed in time. But he's like, oh, I'll take them. And it turns out, thank you, Cal Still, this is the person I got all my methods training from at Nebraska. His wife put herself through college sewing for people and doing alterations. He took my pants home to his wife. She fixed them for me. He dropped them off at the hotel, and I wore them the next day without incident. So the moral of the story is bring 2 suits or a sewing kit. I told this story to a friend of mine, and he told me a story of going on internship, going to the bathroom before his day was to start, and the button to his pants dropped off and fell down the urinal. So he went to their main office, asked for a stapler, stapled his pants shut, and went about his interview. So, tailoring is important. Making sure your pants are big enough so that they don't split open, also important. Apparently I had done some stress eating over the holidays, not to say. But it ended up okay. I got the job at Nebraska, and that's where I went. I did get the job actually at Syracuse too, but I decided not to go there. I did not get the job at Penn State, which was the most awkward thing ever because everybody knew it, and I showed up to teach my class the next day, and it was like dead man walking, you know. But it worked out for the best, I think. But it was just a very awkward situation. Comments from the Zoomers. 10 flushed a mermaid earring down the toilet once, and she said it returned to the sea. That's nice. Yeah. Also, another tip, if you're going to not wear your suit on the plane, make sure you're wearing clothing that is suitable for a job talk for when they lose your luggage. The person who interviewed at Nebraska the year after me had his luggage lost. Unfortunately, he had the wherewithal to have worn like, khakis and a button down or something that would look presentable on the plane. So don't wear your sweatpants to your job interview, just in case they lose your suit. Or you rip it open because you did too much stress eating. Let's see, another Zoomer says, I've split my pants 5 seconds before going on stage for a ballroom performance. Oh, that is much more dangerous because you really need pants to function if you're twirling around the stage. I mean, I could have just stood there with my butt open, like, with my back to the wall or whatever, but walking around and talking to people, that wouldn't have worked. So, tailoring, that's what we're doing here. We are tailoring our pattern of variance and covariance into what we need it to be. And splitting out the main reason that we would need the tailoring, the part of you that's the biggest, fixing that by solving the problem, sticking it in the G matrix, allows us to kind of customize what's left. Take it in, take it up, take it out, whatever you need to do. Deal? Okay. I think, is that enough for now?
Can I ask one clarification?
Yeah, let's keep doing questions. That's much better than doing more stuff.
So the unstructured in and the unstructured in -1 are the same because they both fully describe the data.
Yep.
And the compound symmetry in the R only model and the compound symmetry in the G plus R model are also the same because they both include a random intercept. It's just whether the random intercept is in the R model or in the G model, and then it ends up in the V model.
Yes, that is an excellent point, and I'm going to make sure that I can repeat that for the audio recording. So this, here we go, these two. This is the end result either way. If you are doing compound symmetry, then this is the direct result. You have your CS parameter, which is a random intercept variance, your residual variance parameter, they're all in one matrix. Unstructured, let each variance be what it wants, each variant, let that. If you take the random intercept out of here and stick it in G, then what's left is a diagonal matrix, zeros everywhere else. Here, you can take the random intercept variance out, and then these terms refer not to the T1, T2, T3, but E1, E2, E3. And the last spot in here has to be 0 to leave room for the random intercept variance to have something to do.
So would it be fair to say that in the R-only models and the G and R models, the bookends are the same, but the models in the middle are the ones that are different?
The way you get there is different. It's different routes to the same place.
Okay.
So if you don't have a separate G matrix for level 2 variances and covariances, then R and V are the same thing.
Okay.
If you do, then G and R put back together again is V.
Okay.
Yep, and so the endpoints, they are exactly the same. It's the things in the middle have differences based on whether you've controlled for the intercept and stuck it someplace else or not. Yep. Okay, other questions? The rest of this semester, we're going to do GNR. Welcome to the jungle. We got fun and games. Yeah, they're groaning. Oh, come on, that was funny. Would you prefer a different version? How about salt and pepper? Let's talk about fit, baby. Let's talk about R and G. Let's talk about all the variants and the covariants that make V. Hey. We can make this fun. Yeah, no, don't clap for that. Don't encourage me. This makes it worse. So yes, G and R put back together again is V. Whatever song you want to sing in your head for that, knock yourselves out. All right, let's call it a day then. How about that? Give you 5 minutes of your life back. Let me know if you need anything. You can be working on your formative assessment. The last 2 questions you should be able to answer. And you can start working on homework 1 if you want. Due next Wednesday. Okay? All right. Thanks, Zoomers. Thanks, Roomers.